All right, welcome to Lean Together 2025. Right now we're going to have Joseph Tooby-Smith speaking about physics and lean. Go ahead, Joseph.
Yeah, so unlike most people that perhaps do lean, my background isn't in computer science and my background isn't in mathematics. My background is in physics. And I want to talk to you a bit about where I see the interaction between physics and lean going in the future and some of the work that I've done in this direction. So I wanted to start with a vision of what I believe lean and physics could look like in 10 years' time. And I'm going to start with the obvious one, the obvious point, which is to say that hopefully there should be a repository like MathLib, but for physics. And this repository should contain a number of things. So in the same way that MathLib contains fundamental theorems and definitions for mathematics, this repository should contain fundamental theorems and definitions covering physics. So not after a specific target, like for example, the Fermat theorem project, but more like a monolithic library covering a range of different areas in physics where you can use theorems and definitions from different areas. But furthermore, it should allow a way to interface with programs and simulations. So physicists, they like writing computer programs, they like writing computer programs to prove things, and they like doing simulations because that is what we're trying to do. We simulate things related to the real world. So having a way to go from the fundamental theorems and the definitions, really the definitions, to something that you can put into programs in a nice, easy way would be nice for such a repository. And this could be made possible with computable and efficient definitions. So making sure that the definitions that you write in such a repository are computable and they run efficiently. But it could contain more. So ideally, in 10 years' time, we may be able to have an interface between experimental data and formal theory. Because after all, physics is about the real world, and it's about experiments and experimental data. And when physicists come up with models and theories, they use their theories, they test those theories, either explicitly or implicitly, against the real world. So some way to take fundamental theorems, to test those, to feed experimental data into those, come up with predictions would be great. I have no idea if this is possible, if you can do this. This is a vision of what I want things to look like. And it should contain extensive physics-based documentation to make it easier for people to learn about these areas of physics. They should be able to take a file in such a repository, read about the definitions, read about the lemmas, and why they're of interest to physics. Kind of in the same way that if you know lean and you want to know about an area of mathematics, you can choose a file in MathLib and you can go and read that file and you may get a good understanding of what sort of things have been proved in that area. And this is perhaps somewhere where AI could come in to help write the documentation. Of course, AI can be used, as we all know, very extensively in Lean to do a lot of other things as well. This repository should probably satisfy a number of other conditions. And most importantly, it should be useful to the uninitiated. So I don't know many physicists that would be willing to learn Lean. And if such a repository is ever going to take hold in the physics community, it has to be useful, at least initially, to those physicists that don't want to learn Lean. And there are a number of ways that you can do this. So it could be organized by physics principles in the sense that MathLib is organized by mathematics. It's got files for like category theory, topology, etc. This repository should contain things organized by physics. It should have a file for condensed matter physics. It should have a file for the Higgs boson, for fermions, for the Lorentz group, etc. It should be easily searchable, akin to Lugo or Lean search. So it should be possible for somebody to find a search engine for such a repository, write, for example, Higgs boson into that search engine and be given everything in this repository about the Higgs boson. And it should look like physics. A physicist should not be scared to look at the code, the lean code in such a repository. It shouldn't put them off. They should kind of understand what's going on, the same way that a mathematician can kind of look at code in MATLAB, and perhaps they may not know lean that well. They could probably understand some of the theorems and some of the definitions. And there's one other thing in this vision, or my vision of what I want the interface of physics and lean to look like, but I'm going to leave that blank for now. And I'll come back to that at the end. So over the last year and a half, I've kind of been trying to make this vision a reality with a project called HepLean. So HEP stands for high energy physics. If you don't know what that means, it's just fundamental physics. So any question about the nature of the universe, laws of physics, what's the correct mathematical framework for physics, what's gravity, all of that falls under high energy physics. It's a very broad area. And so this is a repository, a monolithic library for results in high energy physics. And it's my attempt at this vision that I talked about on the previous slide. So let me talk about some of the things, how this HepLean satisfies certain conditions that I put on this vision. In particular, let me talk about the fundamental theorems and definitions that it contains, which cover in physics. I'm not really going to go into much detail into a lot of the other things. There are other people that are much more interested in the interface with programs and simulations and sciences than myself, but they're all scope for future work. So let me talk about the fundamental theorems and definitions covering physics, which are currently in HepLean. So let me give you some stats. HepLean contains about 1,000 definitions and about 2,000 theorems. So it is by no means the scale of MATLAB, which contains about 80,000 definitions and 160,000 theorems, but it's also not really a small project. It's got about 200 files in it. And these cover a range of different areas and a range of different topics in physics. In particular, here is a graph. It is a completely made up graph that I made on PowerPoint. So don't think too hard about the scales or anything. It is wherever I put a point. But it shows you roughly the areas covered in HepLean and kind of what coverage they have. Now, I realize that most people in the audience are probably not going to be physicists. So let me just go through these very briefly. But if you don't understand any of this, don't worry. My point is that it covers currently a fairly diverse range of topics in physics. So the biggest peak here is ACC, and that stands for anomaly cancellation condition. And what this basically is that you can associate to each particle in the universe a charge. Like the electron has negative 1 charge under the electromagnetic group. It turns out that you can't assign charges to particles arbitrarily. You can't assign, for example, an electron a charge 20 and a quark a charge 300. There's certain conditions that have to be satisfied. And those conditions take the form of Diophantine equations, so polynomial equations in the integers. And HepLean contains the solutions to a bunch of these equations related to real-world physics applications, and these are research-level results. So these equations are much easier to solve than, for example, Fermat's last theorem, basically because we know they have solutions. But this sort of area is basically number theory. The Higgs potential, so the Higgs boson was the last particle that we found at a particle collider. We found it in 2012. And it is what gives other particles mass. And it does this via its potential, which has a minimum. And so HepLean currently contains properties of the Higgs potential, including its minimum. And this is basically finding the minimum of a function and symmetry properties thereof. HepLean currently contains things about flavor physics. So you may know that atoms have a nucleus at the center, and that nucleus is made up of things called quarks. The quarks mix with one another, and that is determined and that is controlled by something called the CKM matrix. This is a 3x3 unitary matrix defined up to an equivalence relation. And HepLean contains properties of this matrix. It contains stuff about the Lorentz group. So the Lorentz group is the symmetry group of special relativity, is the symmetry group of spacetime, probably the most important group in physics. And HepLean contains the definition of the Lorentz group and topological properties thereof. It doesn't contain any Lie group properties. The Lorentz group is a Lie group, but it doesn't yet contain, HepLean doesn't contain any Lie group properties thereof, just topological. It contains the definition and properties of fermions. So fermions make up most of the elementary particles that we have in the universe, except for the Higgs boson. And they are defined as a representation, or as really as a projective representation of the Lorentz group. And HepLean contains the definition and properties thereof. Perturbation theory is used in physics to do something called quantum field theory. Quantum field theory being a generalization of something called quantum mechanics. The most important theorem in perturbation theory is something called Wick's theorem, and HepLean contains a proof of the static Wick's theorem, and it's very almost going to contain a proof of the time-dependent Wick's theorem, which basically allows you to write down these things called Feynman diagrams, which are little cute diagrams with arrows and squiggly lines which show particles and are kind of the image you see when you search for particle physics. And then it contains some informal results related to BSM physics. So BSM stands for Beyond the Standard Model, which is our current best, the standard model is our current best model of the universe. BSM physics is basically when you add particles to the universe and you see what happens. And HepLean contains informal results of relating to BSM physics. And these are results kind of similar to what we saw earlier today, which are like informally written in the Lean code. And you can go and formalize them. And there's a graph on the HepLean website where you can look at all of them and you can see if you want to take a go and formalize them. And then on the right, I've written something called index notation. I'm going to come back to that in a second. But let me turn track a bit, and because we can ask a question. We can ask a question which is, so all of these things have been formalized into HepLean. There is a general question of whether it is easy to formalize physics into something like Lean, while still being useful to the uninitiated and while still being useful to the physicist. And I'm going to argue that there are unique challenges to formalizing physics that don't come in when you formalize in mathematics. And these challenges are basically down to the fact that physics is not maths, and probably more importantly, the physics community is not the maths community. So if you're trying to formalize something for the physics community, you really have to think about what the physics community wants, compared to thinking like a mathematician. And the biggest challenge is kind of something that we have seen throughout this workshop, and that is the difficulty that it takes to formalize definitions. And this is somewhat of a artificial illustration of this and how this affects physics. So for some physical quantity X, there may be some maths definition, and that maths definition lives in a space of definitions, doesn't really exist, it's just an illustration. And that maths definition may sit outside acceptable Lean definitions. So you may have to do some work to turn that maths definition into a Lean definition, into something that is acceptable to Lean, not only acceptable, but that works nicely and that doesn't get you in type-dependent very hell, and all of that. Now, more often than not, if this quantity X is a physics quantity, the physics definition is way over there somewhere. It's nowhere near a definition that the mathematicians would accept, let alone a definition that you could efficiently put into Lean. And one has to do some work, either to turn that into a maths definition or to turn that into an acceptable Lean definition. And one can make a whole career about taking things in physics and writing them using clever mathematical techniques, so that they are understandable to the mathematicians. But my point here is that often the physics definition, you have to do a lot more work to get to an acceptable lean definition, because there often isn't even a formal mathematical definition for a lot of the physics quantities at play, and not a maths definition which is useful to the physicists. And you have to do all of this while still being useful to the physicists. This kind of idea has come up in the lean SULIB in the form of discussions around units. So the physics definition for a unit is fairly, we kind of know it, physicists know how to work with it, but it's quite far away from something that a mathematician would perhaps accept as a rigorous definition of a unit. And you have to do a lot of work either to turn that physics definition into a maths definition, or more importantly, to turn that physics definition into an acceptable definition that you can put into lean. There are some other challenges when it comes to formalizing lean. When it comes to formalizing physics. So let me discuss some of those. The first one is paper style, and you're going to have to squint a lot to see these. But the paper on the left is a maths paper. Sorry, the paper on the left is a physics paper, and the paper on the right is a maths paper. So the paper on the left is written like Moby Dick. It's written like a novel. The paper on the right is written like lean, or rather lean is written like a maths paper. When you're trying to formalize, if I gave you all the option to try and formalize one of these papers, I can guarantee most of you are going to choose the one on the right, basically because it's already laid out like in the same sort of structure that you would try to put into lean. Whereas if you're trying to formalize the thing on the left, you're going to have to do a lot of work parsing where the theorems are, parsing where the definitions are, if they're even there in the first place. And this is even true for papers in physics, which are really very mathematical. So the paper on the left is actually about infinity topos theory and how you can do quantum field theory or explain some things in quantum field theory using infinity topos theory or infinity categories. Very mathematical, but written for the physics community, and therefore written not in the style of lemma's definitions and theorems, but in a more prose style. The second challenge is that physicists really like imprecise results. They like taking terms to be zero because it makes their life easier, and they know intuitively that taking that term to be zero isn't going to make a difference to their calculation. This is kind of how physicists operate and how they work and how they produce papers, and that makes it very difficult to formalize some of these things into lean, because you have to deal with these imprecisities and somehow work around them, if they can be worked around at all. If this is even just assuming what the physicists are doing is mathematically correct, which sometimes it may not be. The third thing is that physicists care about specifics and not generalities. So they care about 3x3 matrices with specific numbers in and the ranks of those matrices. They don't care really about n×n matrices and the property that they have ranks. And lean sometimes struggles with specifics when you need to deal with more concrete objects. It's sometimes better at the more abstract stuff when you can use induction or other general principles. So this can be a challenge, especially if you want something that's going to be of use to the physicists, where they actually do care about the specifics and not the generalities. And lastly, something that I have kind of alluded to in the vision that I gave, physicists really like long computational and experimental proofs. They like taking a computer program and running a search over a discrete space, for example, and using that as a proof of they use that as a proof that you can have a certain finite number of instances of something. And this often involves large data sets. Even the result contains large data sets. And sometimes they use, as I kind of alluded to, experimental proofs, which is somehow they feed experimental data into their proof somehow. This is done at the more minor scale of saying like experiments tell us a term is zero, to a very large scale where lots of particle physics is done by assuming that you already know some experimental data. So there's some of the challenges. Let me return back to the fission and discuss how you make things look like physics. So how do you ensure that that lean in a project like HepLean, which is for the physicists, how do you make that look like physics so that the physicists don't get scared about it? And this really comes down to this peak on the right-hand side of this diagram, which is about index notation. So index notation is a way that physicists and some other people deal with tensors. And here's an example. If you look at the equation at the middle, this is an example of what index notation looks like on pen and paper. So sigma and epsilon here are tensors, and the alpha, beta, and nu indices, and the alpha prime and beta prime indices are basically telling us how we should think about these tensors. So sigma is a rank 3 tensor, epsilon is a rank 2 tensor. And you can see the two new indices, or on the left rather, the new index appears twice, and that implicitly to the physicist means that index is summed over. Furthermore, notice that on the left-hand side of the equations, the alpha beta and alpha prime beta prime are in a different order to on the right-hand side of this equation. The point is that physicists use this notation because it is easy. If you wanted to write down this equation in terms of tensor operations, so like gradients of tensors in an appropriate category or something, then the equation would be massive and it would be really difficult to work with. So you want to make that look like clean, so the physicist doesn't get scared, basically, and you can work more efficiently. So HepLean contains an implementation of such index notation. You can see what the equation in the middle looks like in HepLean. You can see that there's two new indices, which are contracted automatically by lean, and the fact that the alpha prime, beta prime on a different order of both sides of the equation is also taken account for by lean. So the physicist can write stuff or can read stuff in a way that looks like physics, whilst lean in the background doing the difficult work and writing that out explicitly. So that's kind of how you can get things to look like physics. So let me talk about this last thing. I'm going to quickly escape because I don't know what time I'm at. Okay. So let me quickly talk about this last box in the bottom right-hand corner. And there's one part of this fission which I haven't discussed yet, and I think it's the thing that made really MathLib a success, and it's really the only thing that would make a project like this a success, and that is that it should have a large community behind it. Because this is not the sort of project that one person could do by themselves, and it's not the sort of thing that can be one person's project. So if you are interested in getting involved in anything related to like formalizing physics, formalizing science, reach out to either me or there's a bunch of people on the Lean Zulip that are interested in this directions. And in particular, any help with these three things would be great, especially making Lean more searchable. And there's obviously the more standard stuff that documentation needs to be written. So if you're a physicist or know physics and you want to get involved, but you don't know Lean, or you don't know Lean so well, come write some documentation. There are these things called informal lemmas that are kind of akin to what we saw earlier, basically informal string literal statements written into the Lean files, which form a nice graph on the HepLean website, which you can come and formalize. Help with Golfin for infrastructure. And generally, if you don't have time for any of this and you still think it's a good idea, maybe you don't think any of this is a good idea, but if you do, help with promotion, like if people say they're interested in Lean and perhaps they have an interest in physics, pointing them to projects like this would be great. So with that, let me thank you, and I'm happy to take questions.